Cześć i witam na kolejnej prelekcji. Przepraszamy za opóźnienie, natomiast poprzednia była bardzo energetyczna i ciężko było przerwać chłopakom, natomiast teraz zmieniamy znowu obszar i w związku z tym, że prelekcja będzie poprowadzona w języku angielskim, I will switch another time into English and I would like to announce Grzegorz Ochmański, who is a solution architect in Amazon Web Services. And Grzegorz will talk about building and scaling permanent worlds for MMO games because this requires a different approach toward the game backend and many other things related to MMO games from developers' perspective. So, Grzegorz, the stage is yours.
Thank you for introduction. Hi, I'm Greg, as it was said, and I'll have a pleasure to talk about the MMO games and the MMO worlds. So let me start by maybe not jumping directly into the digital worlds and our digital simulations, but about our current world. So our current world we are seeing around us and we perceive with all our senses, especially when we see it, it's that fast and responsive just because the photons are traveling so fast with the speed of light and bouncing through the surfaces of the objects, and we don't feel a lag, right? So I want to keep this in mind once we jump into the more advanced subjects into the presentation. Unfortunately, unlike our current world, the requirements of the network and our code technology is lagging behind that. That's why we have to rely on the networks and actually the technology TCP and IP that has been invented in the 70s and upgraded ever since at that time. So about the persistence and the permanency of the words in persistent words, in fact, let me start that we have the avatar, which is Greg, and Greg would like to play a game. This is Greg, and he would like to play a game like the simulation, because in fact the games and everything that happens within digital world is a simulation, and we use the simulation tools like Unreal Engine, Unity, custom engines that simulate physics, simulate the situation, heats, etc. Raycasting, particle physics. So Greg would like to play a game. So Greg jumps, connects starts his client, he connects to a game, he has created his avatar, he plays the game. But what happens when the Greg disconnects? When the Greg disconnects, when in the situation of the persistent world, the world continues to live, the events continue to happen, the players change the world and shape the world in the simulation to look differently. So when the Greg jumps back to the game, he is not seeing the same state of the game. So in fact, what does it tell us about the entire world and the entire simulation? That everybody is a late joiner because nobody is connected from the very beginning once the server was started and the simulation has started. So everybody is a late joiner. It's important about to remember about it in the later step. And of course, anybody can hop in and hop out of the simulation, and the world continues to live and evolve. So the permanency is very important characteristic of the world. This permanency as a mechanic of the world, because that's how we can create the immersive experiences. Imagine that there is forest, right, of all trees on the map. You see it, you play, but you hop in, hop out, and next time you see that the forest is there no more, because essentially there was a quest when you were not playing, and all the trees were chopped down, and you come back and you see, okay, this is not here anymore. Maybe I need to wait till the trees sprout again, and so on. So this permanency gives us the feeling that the worlds are immersive and that we can relate to this world, because this mechanic is very similar to what we see in the world, in our world around us, and what we are used to see. So why does it happen, right? The Greg would like to play a game, but what happens that that time when he starts his client, he connects somewhere and starts basically playing. We need to reach a state like looking from the pilot view and from the very high level, we need to synchronize the state in between multiple compute units. Like, how do we do that, right? We are still bound to the laws of the physics, so we can't even the light in the fiber is not traveling at the full speed of light in the vacuum, but like around 80% of the time. And the compute units might be so far away that even the connection over the fiber might not be perfect, right? So we don't see and feel that world immediately like we see our world around us. So what we have to come up with is the tick rate. In fact, the tick rate is maybe if somebody was playing a lot of Counter-Strike or other FPS shooters, might be familiar with the topic. In fact, this is just how often do we refresh the state of the simulation. To reach that sync, we need tick rate over the unreliable network, such as internet, to reach other computing units and get the information back from these computing units at the given rate, meaning usually measured in hertz, because that's the number of occurrences within a second, how often that is being refreshed, or how often this portion of information is received and sent by us or exchanged between two computing units. So in fact, from the ancient times, but still used today, we have the idea of deterministic lockstep. That's one of the techniques how to reach the state sync. And it's deterministic not for a reason, right? So the determinism means that for the same inputs, like our strokes on keyboards, moving forward, backward, left, right, the simulation will produce the same outputs on our screen, meaning moving left, right. And what does it, in fact, this determinism tells us that the simulation, in fact, is run at both ends. It's run at the client side as well as on the server side, and each and every client that connects to the simulation, they run their own simulation. We just synchronize the state of this simulation by providing or mimicking the same control information. So we just send forward, backward, and so on information about the unit. So what it helps us to achieve is that our simulations will be in sync, because we are sending again over the network this commands. But what happens that if some of this information is lost, right? The internet is not reliable connection. That means that this information needs to be sent back, because again, we need all of the inputs, so our simulations, they stay in sync. Also, as we are waiting for all the clients need to send the inputs before our simulation can render additional frame, additional step, they need to receive all of the inputs from all of the clients connected. And this means that actually the slowest ping is everybody's ping, right? Because we need to wait for always the slowest responsive client. And with having that in mind, that means that we can't receive the high refreshes or high frequency of our ticks. So actually going beyond 10 hertz, so 10 occurrences each 100 milliseconds, that's actually quite hard to achieve. So this is usually used for 2 to 4 players when we are synchronizing the state between 2-4 compute units, or 2 or 4 players, because reaching the higher number, and of course reaching higher number population of players, means that we will need we will have more occurrences of the situation. There are very long response times. So on the other hand, what we have there is also not so slow, new technology, which is snapshot interpolation. What it is, right? So the sticks are the snapshots, the snapshot state of the simulation that we are seeing or that we are sending. But unlike with deterministic lockstep, only the server runs the simulation, while the dummy clients are just rendering what the server tells them that they are able to render. This means that the authority of all the simulation lies within the server. This helps us, of course, prevents from cheating, and helps to maintain the simulation state, but it's for sure not deterministic. This authority of the server is within its own, so it runs the simulation, and we are just merely receiving this this information. But as the snapshots are received within the period of time, within a second, right, the number of those snapshots within the second, our client needs to interpolate, meaning generate intermediate frames in between those snapshots. So usually when we think about it, we can't really think, or this technology can accept loss of some of the snapshots, because if we are interpolating between two snapshots, usually this is called LERP, the linear interpolation. We can lose 1 or 2 frames and we are still able to render. Maybe there will be some choppy, maybe there will be a little longer animation, it won't be so precise, but in generic terms, we can do that. So usually when we think about snapshot interpolation, we don't talk TCP networks, because with the TCP networks, you would have to wait for the retransmission if something is lost, and that actually, instead of just rendering, just skip that, let's keep rendering, we would be waiting for that input. And it's not that important, because again, we don't run simulation at our client side, because the simulation is run at the side of the server. Okay, but this creates some issues, right? And let me take you back to the wonderful example of the 64 Hertz the tick rate with the simulation. So we know that the between the ticks we have around 16 milliseconds. So what happens if we add a bit of the latency monster to it, and we see that now our round trip time from our happy client to our happy server, because servers are always happy, is 100 milliseconds. So this means that when we press the button, and remember the servers are authoritative, if we press the button, we have to wait for the server says, yes, you can move 1 unit forward, or you can move 1 unit left. And that would create a very laggy experience for the player and for the user of that simulation. This means that we need to somehow hide again, and we need to somehow fight the latency monster. And how this is being done is that we are always cheating a bit with these online games. So there is an idea of that reckoning, or the client prediction, that the client says, okay, dear server, I'm moving to the left, and immediately starts rendering, so the player feels that movement, that he's really responsive and his tractor is moving. But the server receives this information 50 milliseconds later in this example, half of the round trip time, and tells, for the 99% of time, a response is responding to a client that yes, you moved 1 unit to the left. But what happens if that's not always the case? So the client starts rendering the prediction that we moved 5 units to the left, sends this information to server, and server runs its own simulation, says, no, you just moved just 2 units to the left, or you moved 5 units to the right. In that case, we would see all this teleporting over within online games, which you probably, if you ever played, you've seen the laggy players, that they teleport sometimes. It's happening because of the prediction. So the client thinks that, okay, I moved 5 units, 10 units in some direction with some velocity, but the server tells him, no, you have to correct your position. And the clients, of course, need to listen to the server, because server is authoritative and he has the last voice on what has happened. So the latency is your enemy, it's not your friend. And the snapshot interpolation buffer is there because normally you don't immediately start rendering the information you receive. You would like to keep it in the buffer, in the cache. So whenever something is lost, you still have 2 points which you can render in between, so you can generate those intermediate frames for the simulation, for the rendering. And there is where it all gets complicated. This is not the situation when you get the 360 no scoped in the Counter-Strike. But the situation that often happens, that people think, okay, there was a cheater. It's not necessarily always that. Probably you might heard about it. There is a lag compensation. So for our case, let's think about the issue. To understand it, where this issue arises, let's consider an example shown here. The player A and the drone in the black color is shooting at the player B, the blue one, who is moving behind the wall for cover. However, due to the network latency, again, latency monster, player A shots might arrive at the server, because remember the tick rate and the latency. They arrive at the server after the player B, who has lower ping, has already moved behind the wall or behind the cover, right? Without the lag compensation, of course, the game server would register the shot as a miss. You know, it would it would perform the calculation, raycasting, and we say, okay, you missed, right? Although you had it perfectly in the sight, you know, all the cross, it was next to you, you couldn't miss, right? But you missed. So it would be very frustrating. So with the lag compensation, the game server, as it's authoritative, right, and it receives all the inputs from all the players, is able to predict, like rewind it back in time, because it received information with the timestamp when you pressed the fire button, and it's able to rewind that simulation and the position of that player, because again, it knows its inputs and knows exact location on the XYZ axis where it was, and it's able to, at that split of millisecond between ticks, it's able to predict, okay, raycasts, you had the hitbox and you had the hit. Of course, that will result in the situation that might feel unfair, that you hide behind the wall, but at the same time, we can't favor in online games the people with the lowest ping. This is especially visible when there are huge differences, when you have like 10 milliseconds ping to the server and the latency, the round trip between the server and your client, and somebody has like 500 milliseconds. It starts to be really visible above 250 milliseconds of the round trip time. And it's all for fighting the latency monster, and it's usually calculated as the current server time and minus latency of the client and minus the interpolation buffer, I should say, on interpolation time, you know, those 2 frames in between, which you keep in the buffer, because that actually adds to your lag, right? Which we try to hide with, again, the dead reckoning or the client prediction. And now where it really starts to get more complicated. So what we actually send in those snapshots, right? I said so many times, we send snapshots over the network in the tick rates with given rate over the network, but what actually we're sending? So as we are sending snapshots, so actually in 3-dimensional space, we need to send the current position, which is usually encoded with XYZ axis, right? 96 bits, because that takes 3 floats to encode. We send the velocity vector, meaning the XYZ over time, how fast and with what velocity we are moving. So the server and the client, the server can calculate where we will land actually. In each, of course, that's why we need 3 floats for velocity vector, because we can move in each of the directions, right? Along the x-axis, z-axis, or y-axis. So that's why we need 3 floats for that. And the most important one, and probably the most complicated one, is quaternion for rotation, often called quads. And for that, we need this is to rotation. And if you're familiar with the Unreal Engine terms, you can translate the rotators to quads, and this is what it is. The quads are actually the rotation of the object in the 3-dimensional space, and you need a lot of floats. So for floats, because you need to have that rotation axis XYZ, of course, and the rotation of that body, of the rigid body within the 3-dimensional space. That's why you need 4 floats for that. That give us a bit of 320 321 bits for each of the objects. And remember that we are not rendering just, the server is not sending only position of one object. All objects that are moving, they are 321 bits minimum, right? Plus other, sometimes the elements like actors, they can be composed of multiple of those objects that are rotating in the three-dimensional space. That's why we need more and more data to be sent to us. Quickly calculating with 2000 objects being sent from the server for 200 players. Remember, we need to multiply because this is just one client connected. We need more, like 200. That already gives us a very unsatisfying number of 12.8 gigabits per second. So this actually a bit more than a typical server can have in the network, network adapter connected. But fortunately for us, we have a few techniques that we can use to actually cheat a bit, and the games are always cheating. So usually we are sending the updates modified according to our client view distance. So the farther the objects are, the less frequently these are being refreshed, or the slower they tick for us, because it doesn't really matter if we see some object like very, very far away. For our simulation, doesn't really matter if it ticks at 8 hertz or 128 hertz, they won't be noticeable, right? So we are a bit cheating here. And of course, something that it's very close to us, we need to refresh it at the highest possible rate to simulate the physics, simulate all the all the collisions and the word around the avatar. So the farther we are, the less information is being sent. And additional things are, of course, compression and the bit packing. So we are able actually to get down this 321 bits or 4.1 kilobytes per second. We can actually get it to a very satisfying number of 25 bits per second, and still encode the same information for server to process. But before that happens, before we can saturate the network with all the optimizations we can introduce, we'll probably run out of the CPU and memory on the server rather than we will run out of the bandwidth. Okay, so summary on the building. These are some building blocks. Of course, if you will be using Unity dots or Unreal networking, you won't see this all, but it's very important for you to understand how this works when you start troubleshooting and something is not replicating, or it introduces, even within one PC, it's introducing very high latency. You need to know how this works to actually find and spot an error. So the summary on the deterministic lockstep, this is more usually for RTS games, StarCraft 2 or Heroes of the Storm. This is where we usually use the deterministic lockstep. So we receive all the inputs, we send it to all the clients, and everybody simulates the physics. Snapshot interpolation, we receive snapshots, we try to interpolate in between them, so generate intermediate frames, so continue to give that idea of smoothness of the movement of objects being rendered. That reckoning, usually this is the client prediction, so we predict where the client will move without waiting for the server, and then server corrects us and we are teleporting all over the place in case our client predictions are wrong. And the tick rate, of course, which is the almighty tick rate, that this is the frequency on how often the physics, how often the simulation refreshes its state. Okay, but the scaling up. So until that time, we are still talking about a map, a world, a simulation that is consistent within one server, and but there are limits, right? We can try to optimize that. We can try to throw the AI to a separate thread. We can run the multi-threaded physics, but soon enough, if we plan for a scale, we will hit that our server is not big enough. We can simulate how many, well, like 100K objects in like medium server, 200K objects in like already a large server, maybe 300,000 objects with a really big server. But if you would like to go to millions or tens of millions of objects being simulated in the world, like how do we do it? even with all the optimization, we will run out of the bandwidth, CPU, and the memory. So there is a help with that, and it's called spatial partitioning, and a very hot topic recently. But like, why do we do it? Like, especially for that we need to somehow narrow down the number of the collision detections we need to distribute this load within the best possible situation, as it would be in a cluster between all the computers connected working in the grid. Okay, so usually this is how we do it. We run spatial partitioning that helps us to divide the population of the one big simulation to a smaller chunk. So each server again remains authoritative over the objects that it's using, and at the same time we are distributing the load, because again there are multiple servers cooperating, not the single one, so we don't have the bottleneck. This was something actually implemented in the Amazon Game Studios, the new world map, and this is how it looked. So they used the EC2 from AWS, the Elastic Compute Cloud, like virtual machines in the cloud, think about it like this, and they divided. Those visible tiles are the spatial partitions. This is not the grids and the cells already, because those are smaller and not visible here, but this is how they partition the world across different servers. But we need some smooth movement, right, within our one large simulation, and unlike sharding that was introducing multiple different simulations, this is one big simulation. We need to fluently and then smoothly transition between the servers so players don't notice that they moved from server to server. So what do we do? There's one of the technique called the grid partitioning. So we divide the entire map, whether this is 40 by 40 kilometers in the game world, we divide it to the set of grids, and we give the sum of this grid cells, we form the partitions of multiple grid cells, and we give this partition to authoritative server, and the server is authoritative over set of the grids. It's now its coordinates. And additionally, what do we do? Because now we don't have to simulate the physics is entire world, because it would be impossible for each server, but we only simulate the physics in one grid cell, and we can divide it further because we can use the binary space partitioning, coordinate hashing. Coordinate hashing is usually used by the MMORPG games with the hash tables, and we can further divide this three-dimensional space with quad trees and oct trees. Basically, it's all to narrow down the possibility of the objects colliding. So we can detect really this collision within the grid cell or very small cell rather than within the entire world, because of course, if their objects are within two different cells, they can't collide between each other. So it's pointless for us to spend our CPU cycles for that. But of course, as these grids and these partitions, they introduce a new issue that when you try to transition, think about it, if you are having a fox and a rabbit, and those are in different partitions, meaning those partitions, they are different authoritative servers, but you have one map view, right? And the rabbit and the fox are standing next to each other, they don't interact, right? We need to have some way how they communicate. And this is solved by usually the subscription area. So each of the partitions is kind of extended. Think of it as of the lines that are beforehand, before that partitioning physically, let's say, happens. We need to have a line where we inform the other server, okay, this object is very close to transitioning between the boards. We need some RPC call. Usually would like to have some placement group. The servers cooperating in the cluster needs to be very close to each other, so you have minimum latency for your RPCs, and you can use Redis RPCs, gRPCs, something that provides you almost zero latency, and you can reach that with the RPCs because there's even sub-millisecond latency in between those. So you exchange this information about the objects. So AI needs to know about the objects that are close to each other, so it can, if they can interact or not. And this is all done by RPCs in between two different servers. RPCs is remote procedure call. This is executed locally, but realized remotely. So with this subscription area being higher or bigger than the partition, we can go to a challenges of the scaling. So if you know about the spice partitioning, you have this line, you have the cross-server interaction, you do all the handover, which is very expensive because you need to write something to the database. Probably the second server needs to retrieve the inventory from the database. So to cross the servers and these partitions, you need something to the efficient ways to exchange this information. Probably you will need something like DynamoDB or some key value store DB like Redis. Very fast, sub millisecond, probably the best if it could happen. But of course, you will have the problems like overlapping, right? You will have object overlapping in the case on between two partitions, and that's why you need effective load balancing algorithm that, for example, is introduced in the same SIEM Space Weaver from AWS or by Spatial OS. You can realize that authority is decided based on the object location, which server is authoritative about which objects. And of course, this also introduced the very low network latency issue and load balancing on the hotspots. There are some techniques how you can optimize with the help of the artificial intelligence. You know the patterns, how the map is designed, how the avatars are traveling throughout the world, and how they interact between each other. So the AI is then able to repartition the world. So say, okay, this is the grid cell you need to take care of because you're creating the hotspots in the towns and when the merchants are, or maybe when the players are gathering, you need to distribute it somehow. Or maybe you created some logic, some quest that is very often used by players, and you would like to load balance that, and by usage of AI and some very trained model from analytics, you can actually reach that dynamic space partitioning and the grid selection for partitions. Okay, so wrapping up with the scaling up, we can have some servers scale up vertically, but they will run out of the CPU and memory before they run out of the bandwidth. We are, for the state synchronizations, we are in fact using the more than 20-year-old technology to tick the packets over the network, and with the interpolation added to smoothen the movement, but of course introduces the new challenges like client prediction extrapolation and that reckoning being a ways to hide that lag from the input towards before the input towards to our character avatar movement. And of course, the large words, the bigger immersive single simulations with large words need to spread across server clusters. And probably for that, you need efficient way of sending the remote procedural calls across the servers, reliable globally, and single-digit millisecond database to save and retrieve information before the avatar transitions happen. Remember that avatar transitions between the spatial partitions are very expensive operation because you need to write to database and the second server needs to read from database, and you need to decide when to issue this RPC to hand over the authority over that avatar so it can start sticking the changes to other clients. And of course, divide and conquer. So instead of dedicated threads, think more about dedicated servers, like try to dedicate the AI for dedicate a server for AI instead of dedicating just a thread. So with that all, I would like to thank you for attention. And there is, of course, comments and the questions you can leave. So I will ask your questions, and I will be here to answer them. Thank you.
Thank you, Greg, for this amazing presentation. Give me a second, because I don't see any questions at this moment. So maybe some of them, maybe some of them will be, I don't know, in some kind of different way of communication with you, like on social media or something like this. So yeah, we don't have any questions, but thank you for this presentation. Thank you for the whole knowledge about MMO games regarding to development things, and yeah, it was really good presentation.
Yeah, so my pleasure.
Yeah, thank you, and we are going to the next session. So see you.
Thank you.
Bye.